Hello, everyone. Welcome to pre-lecture 6. We're going to be finishing chapter 11.4 today, looking at osmotic pressure, which will be the last of our colligative properties. So in a number of natural and synthetic materials, basically all cells and anything that has a membrane in most cases, um, we'll see things that are called semi-permeable membranes. And so this is membrane shown here where we're separating two things. And so on the left side, we have this pure solvent. On the right side, we have a solution where we have that same solvent and let's say some dissolved species. Again, this could be something like a sugar or salt, really any sort of dissolved species. And this semi-permeable membrane in this example is only small enough or selective enough at the very least to let the solvent molecules go back and forth between it, okay? And so an example of this that probably you're all familiar with is a cell membrane in biological systems. And so basically cells need to be separated from each other as well as just other fluids in your body. And so they have these membranes that only allow selective things in and out. And an example of something that's synthetic could be dialysis tubing that is used for people, of course, that don't have fully functional kidneys. And so you can use dialysis tubing to remove metabolic waste from blood. Um, and so that's just two examples of basically semi-permeable membranes that can be used. And so if we look a little bit closer at this example below, again, we have this pure solvent and a solution that are separated by this semi-permeable membrane. And again, our solvent is able to cross the membrane, but our solute molecules that are part of our solution are not going to be able to do that. And since the concentration of a solvent, pure solvent, is going to be greater on the left side, I know it's maybe weird to think about the concentration of a pure solvent, but of course something that is a pure liquid still has a concentration. And so if it's pure, that concentration will be higher on the left side than the right side, and so we'll get diffusion across that semi-permeable membrane to move more of our solvent molecules to the right side, to the solution, okay? And that doesn't mean we won't have the reverse reaction occurring where we have solvent molecules going back to the right side. It just means that we have a faster net rate of our pure solvent moving to the left, okay? And the result of this net transfer is basically getting a diffusion-driven transfer of solvent molecules. This process is known as osmosis. And so those of you that have taken biology courses, I'm sure have heard of this. And again, our net result is going to be that more solvent ends up moving to our right side as compared to the pure liquid and the solution when they start. And what that looks like is this. And so our overall volume on the right side would go up as more and more solvent diffuses through our semi-permeable membrane, at least at a faster rate, and it will raise the volume level there. And so as that volume level increases, again, this is the volume of the solution that increases as opposed to the pure solvent, it will become more diluted, and this will ultimately result in a difference that we can measure called the osmotic pressure. Okay? As we increase that hydrostatic pressure, the rate of the solvent that is going back and forth, and so we would say that our solvent is going to be faster. When we start with our pure solvent, it's going to be diffusing faster to the right side. Once we reach this equilibrium, we define that as having an equal rate of the solvent going both to the right and back to the left. And so as those rates are equal, once we've determined that equilibrium, we can assign an osmotic pressure that can be seen by the difference in the volume of these two well, I guess one pure liquid, pure solvent, and then our solution. Okay. And we designate this with the uppercase symbol for pi. So I'm sure most of you are familiar with the lowercase symbol for pi, but we designate osmotic pressure with the uppercase symbol for pi shown right there. Okay. And of course, this being general chemistry, we want to quantify this relationship. And so we can do that using this equation where our osmotic pressure pi is equal to mRT. And m is going to be the molarity of our solution, r is the ideal gas constant, 0.08206 liter ATM per mole Kelvin, and T will need to be reported in Kelvin in order for our units to cancel properly and this equation to work. Okay. And so if we apply a greater amount of pressure, so say we had this sort of situation here where we have this osmotic pressure and we measure it, if we apply a greater amount of pressure, then we can perform reverse osmosis, meaning that we push some of this solvent molecule back to the side with pure solvent, and our solute molecules, of course, are still unable to go through the semi-permeable membrane. This is very common in water purification. In fact, for places that are quite arid but next to oceans that have salt water, this is one of the ways they can actually get fresh water is through reverse osmosis, where they apply a pressure to push the water molecules to be pure and separate out the salt molecules. Okay. This is also important, obviously, in biology. So any solution that you put in your body must be what's called isotonic. And that means the same solute concentration as your blood or other bodily fluids. So that's why for any of you that wear contacts, you use saline solution. Same goes for if you were to be hooked up to an IV to replace fluids, you would get saline solution as opposed to just pure water. Because if we added pure water right into our veins, then our cells would become what's called hypertonic or hypotonic, pardon me, where if we were to add more concentrated solutions, so more solute than our blood or other bodily fluids have, we would have a hypertonic solution, and less concentrated solutions would be hypotonic. And this is the actual physical effect that it could have on blood cells, where if we have a hypertonic solution, then we would end up losing water from our blood cells and they could become shriveled. Whereas if we have a hypotonic solution in A here, we would have more water present or a less concentrated solution in our blood. And so more water would diffuse through that semi-permeable membrane of our red blood cells and they would swell. Okay? So those are just a couple of examples of why this osmotic pressure is important, both for sort of societal needs as well as in biology. Finally, I just kind of want to talk through the concepts that will lead to some example problems that we'll do in class. So a reminder that our colligative properties, including osmotic pressure, changes in freezing point, boiling point, vapor pressure, all of those are directly proportional, pardon me, to the number of solute species present in a given solution. So that's important to know if why it's important to know if something is an electrolyte or not. So when it dissolves in water, will it form two species, such as sodium chloride will ionize into sodium plus and chloride minus in solution? Or if it's something like sugar, when it dissolves, will it just stay as one molecule? Okay, so that's something you need to consider. And so when we measure one of these properties for a solution, then as long as we know our known mass of solute that is within our solution, we can determine that solute's molar mass. And so this is an example problem from your textbook. Say that we have a solution of 4 grams of a non-electrolyte dissolved in 55 grams of benzene. And it is found to freeze at 2.32 degrees Celsius. So if you assume ideal behavior, what is the molar mass of this compound? And so you can pause this video now, think through your strategy about how you would solve that. If you would like to see the strategy for how this is actually solved, I would refer you to your textbook. Again, we're in chapter 11.4, but this is essentially the strategy you would want to take. And so you would want to find the freezing point of the solution. So you could look up what's the normal freezing point for benzene if it doesn't have an electrolyte dissolved in it. And then we would find basically the change in our freezing temperature then, our delta T. From there, we would be able to calculate the molal concentration of the compound. This would, of course, require knowing our K sub F. That would be a value you would have to look up. Once we determine our molal concentration, we can determine the number of moles because we know the mass of our solvent, benzene in this case. And then finally, from there, we would be able to determine the molar mass of the compound. And again, if you would like to see these steps played out with the actual math performed, I would refer you to your textbook. Okay. And so we could do the same thing for something with our osmotic pressure. And so say, for example, we have a half-liter aqueous solution containing 10 grams of hemoglobin, which is the protein that carries oxygen in your blood. It has an osmotic pressure of 5.9 torr at 22 degrees Celsius. Assuming ideal solution behavior, what is the molar mass of hemoglobin? And so again, if you want to think about this problem, you can pause the video, but at this point, I will go through the kind of roadmap for how to solve this. In this case, we're given the osmotic pressure, and we're also given the pressure and, or we're also given the temperature, and we of course know R, the gas constant, so we would be able to find the molar concentration. And because we're told our volume, we would be able to determine the number of moles of hemoglobin. Then our molar mass is of course grams per mole. And so considering we started with 10 grams of hemoglobin, we would be able to take that 10 grams, divide it by the number of moles that we found in the sample, and that would give us our molar mass. This is another example that's worked out in your textbook if you'd like to see the math performed as well as check your answer. Okay. We'll also be doing another one of these examples in class on Thursday and going through it together. So I would recommend looking through these problems in your textbook before that, but if you would like to see them in class as well, we will be going over them. Okay. All right, that's all for this lecture. I hope that you have a good day. Please let me know if you have any questions, either by stopping by in the office hours or emailing me. Take care, everyone.